A new mystery is unfolding around the interstellar object known as 3Y/Atlas, and the questions just keep piling up. This object is not slowing down in its surprises. It keeps doing things that shouldn't be possible, at least not according to everything we currently understand about comets, physics, and how material behaves in space. And today, something very specific stands out. If 3I/Atlas is truly a comet, then one of its most visible features, its sunward-pointing anti-tail jet, should have very strict physical limits. Limits that, according to new images, appear to be completely ignored. This isn't speculation. This is physics. Today, Harvard professor Avi Loeb pointed out something that turns this object into a clean, testable mystery. Not a vague one, not a philosophical one. A hard, measurable test based on first-principle physics. So let's slow down and walk through this carefully, because once you see it, you can't unsee it. We now have new images from December 27th, and we can compare them to another critical observation taken on December 19th, when 3I/Atlas was at its closest point to Earth. And what these images reveal is, honestly, stunning. So let's begin with the first image, December 27th. Image 1, December 27th. This is the most recent high-resolution view we have. And immediately, one thing jumps out. You see a massive anti-tail stretching in the direction of the sun, not away from it, toward it. That alone is unusual. But the real mystery isn't the direction, it's the scale. This anti-tail is not compact. It's not fading quickly. It's not dispersing the way gas should. Instead, it remains long, narrow, structured, and astonishingly extended, far beyond what standard comet physics allows. Now, before we jump to conclusions, let's establish what should happen if this object is a normal comet. Because comets are not mysterious in general. We've studied them for decades. And the physics of comet outgassing is extremely well understood. What should a normal comet do? When a comet approaches the sun, solar radiation heats its surface. But here's an important detail many people misunderstand. The ice on a comet does not melt into liquid water. It sublimates. That means it goes directly from solid ice to gas. This process is driven by sunlight, and it creates jets of gas that stream away from the nucleus. That gas then drags dust particles with it, forming the familiar tails we see. Now, the speed of that gas is not arbitrary. It's controlled by temperature. At the distance where 3I/Atlas is located, roughly twice Earth's distance from the sun, the physics is very restrictive. At that distance, gas molecules can only move at about 0.2 kilometers per second. That's it, not faster. And this matters because that gas doesn't exist in a vacuum in the way people imagine. It runs into something extremely important. The solar wind problem. The sun constantly emits a fast stream of charged particle, known as the solar wind. This wind pushes outward through the solar system at hundreds of kilometers per second. So when a comet releases gas, that gas is immediately pushed back by the solar wind. This creates a balance. The comet pushes gas outward, the sun pushes back. This balance determines how far gas can stream before it is stopped, dispersed, or deflected. Using basic physics, something called ram pressure balance, astronomers can calculate exactly how far gas from a comet can travel before the solar wind overwhelms it. We've done this calculation countless times. We've tested it on many comets. It works. And the result is very clear. At the distance of 3I/Atlas, gas should not stream beyond about 5,000 kilometers from the nucleus. That's roughly 3,100 miles. Beyond that distance, gas should be gone. Only dust particles, especially larger ones, can continue traveling farther. This is not a guess. This is not controversial. This is textbook comet physics. So now, with that in mind, let's return to the images. What the images actually show. When astronomers look at the December 27th image, they do not see a short, fading, sunward jet that dies out after a few thousand kilometers. They see something dramatically different. The anti-tail stretches hundreds of thousands of kilometers, not thousands. Hundreds, ilex of thousands. That's orders of magnitude larger than what natural gas sublimation allows. And it gets worse. This anti-tail is not wide and diffuse like it should be. Normally, solar wind pressure causes comet jets to fan out, becoming broader and fog-like with distance, but this one stays surprisingly narrow and coherent. That alone is deeply strange. But there's more. Let's compare it with the earlier image. Image 2, December 19th, closest approach. This image was taken when 3I/Atlas was closest to Earth. And once again, we see the same feature. A massive sunward anti-tail, highly extended, highly structured, still coherent, and crucially, still far beyond the 100-mile limit, so now we have consistency. This isn't a one-off artifact, it's not a processing error, it's not a transient event. It keeps happening, which brings us to the real question. Why this is a problem? If 3I on Atlas is a natural comet, then the physics is very simple. Gas from sublimation cannot remain coherent beyond about 3,100 miles. Beyond that point, only dust should survive. So there are only three possibilities, 6,284. We are misinterpreting what the jet is made of 6,285. There is an unknown natural mechanism at work, 6,286. The jet is not driven by normal cometary sublimation. Option 1 would require the jet to be composed almost entirely of large dust particles. But previous analyses already show something odd here too. The dust particles appear to be much larger than typical comet dust, possibly 10 times larger. That's already unusual, but even dust alone doesn't fully explain the coherence and structure we see, which leads to the second option. An unknown natural mechanism? Could nature be doing something we don't yet understand? Possibly. Science is full of surprises, but here's the issue. Any new natural mechanism would still need to obey momentum, energy conservation, and interaction with the solar wind. You don't get a free pass. So far, no known natural process explains extended, coherent, gas-like jets pointing sunward at this scale. Which brings us to the third option, the uncomfortable one. A different type of launch mechanism. Now, let me be very clear. I am not saying 3I/Atlas is a spaceship. But physics doesn't care about comfort. If gas is being launched by something other than passive ice sublimation, something with higher exhaust velocity, then the distance gas can travel changes dramatically. For example, a basic chemical thruster with exhaust speeds of 5 kilometers per s could push gas out to about 25,000 kilometers. An ion-based exhaust at 90 kilometers per s could push material 100,000 kilometers or more. Those numbers suddenly fall into the range we're actually seeing. Again, this is not a claim. It's a diagnostic comparison, and this is why Avi Loeb calls this a clean test. How can we test this? The object is far away. We can't send a probe. We missed that opportunity, but we don't need to. Astronomers can test this remotely. Here's how. If the extended jet contains gas molecules, such as CO or CO2, far beyond the 100-mile limit, then normal comet physics fails. Period. Telescopes can look for this. Ground-based observatories like Keck, VLT, and ALMA can analyze spectral signatures. Space telescopes like JWST and upcoming missions can do the same. They can measure which molecules are present, how brightness changes with distance, whether gas persists where it shouldn't. This is not speculative, it's observational. And if gas is detected far out in the anti-tail, then something is wrong with the simple Comet model. Why this matters? This object is only the third confirmed interstellar visitor we've ever observed, and already it's breaking rules. It's hiding its surface behind a dust veil. Its dust particles are unusually large. Its anti-tail is massive, narrow, sunward, and persistent. Its behavior doesn't match expectations. That doesn't mean aliens, but it does mean we don't yet understand what we're looking at, and that alone makes it one of the most important objects ever observed. What comes next? December 19th was not the end. More data is coming. Observations from Mars orbit, delayed downlinks, spectral analyses still being processed. Between now and March, we may finally get answers. Or we may get even more questions. Either way, 3I, Atlas, is not done surprising us. If you want to follow every twist in this story, I've put all related videos in a playlist at the end screen. And if you want to support the channel, just clicking like or hype helps more than you know. If you want to go further, the coffee link is in the description. I hope 2025 treated you well, and if it didn't, I genuinely hope 2026 turns everything around for you. Stay safe, stay curious, and I'll see you again very soon. Bye-bye.